To finish up the 9.1 to 9.3 class 15. Okay, so also I still don't have the packets. I'm sorry. I will walk down to the duplicating office and figure out what's going on today. So you got to take notes. Class 15 continued. So one of the things that we talked about last class was how the golden ratio derived from deciding where the prettiest place to cut a line into two pieces was. So we had this line, and we said, where should we cut it that's the most aesthetically pleasing? So the ancient Greeks, in fact, it was the Pythagoreans, they said, 1 second here, we're going to cut it so that the shorter piece of the line, we're not going to cut it evenly. We're going to cut it so that we cut the line into a piece that's size 1 and a piece that's size some unknown amount x. And so they said, we think that if we cut it like this, we would really like it because everything that the Pythagoreans talked about and discussed and studied, everything that they held sacred had to do with ratio and proportion. It was their religion, ratio and proportion. So they said what would really be beautiful is if we cut this line so that the short piece to the long piece, the ratio of the 1 and the x, short piece to the long piece, were proportional to the long piece compared to the whole line. So to the Pythagoreans, this would have been divine, right? They would have said this would be to have this cut in such a way would be really beautiful for them. So if I'm going to set up an equation based on this proportion, my short piece is 1 and my long piece is x. And what's the length of my whole line? 1 plus x. 1 plus x. Okay. And then I have a proportion. And to solve a proportion, if you remember from previous class, there's more than one way to do it. But one common way that people are taught is to cross multiply. So you multiply the x times the x, and you get x squared. And 1 times 1 plus x would be what? 1 times 1 plus x is, say it again, 1 plus x. Yeah. Anything times itself is that thing. I mean, anything times 1 is the thing. So this equation, we have to solve it to find out what value of x should be to make the prettiest cut in the line. Now, what we talked about last class is the fact that the prerequisite for this particular class does not include the skill of solving this kind of an equation. So I'm just going to tell you the answer, right? So we do a bunch of work, right? Bunch of algebraic steps, and we should come out with x equals 1 plus the square root of 5 over 2. So this is a bunch of algebra. Yep. And I'm not going to hold you responsible for how to do that algebra. Just know that here's an equation. The solution to that equation is 1 plus the square root of 5 over 2. That's the number that makes my equation true. So let's see what happens when I just type into my calculator 1 plus the square root of 5 divided by 2. So 1 plus the square root of 5 divided by 2, making sure I tell my calculator to do 1 plus the square root of 5 first, right? So I used parentheses in this calculator. And I get 1.61803, and on and on and on. And what is that number? 1.61803 is known as phi. Yeah, this is phi, the golden ratio. So x equals phi. So phi is the number that makes this equation true. X squared equals x plus 1. Right? So if phi is the solution, then when I plug it in, this equation will be true, right? You guys remember checking your work in an algebra class where you take your answer and put it in here? So this says that 1.61803 squared should equal 1.61803 plus 1. Right? When you take your answer, let me just do an easier example. I have 2x minus 5 equals 9. This is easy to solve, right? What do I do first? Move the 5 over, add 5 to both sides. So I get 2x equals 14. Then divide by 2. 2's cancel, and I get x equals 7. How do you check that x equals 7 is really a solution? Plug it in. So I go to my original equation, 2x minus 5 equals 9. I'm going to replace the x with a 7. Does that really equal 9? Well, 2 times 7 is 14. And 9 equals 9. Check. Right? You remember that? Okay, so the same idea applies even when the equation is more complicated. Here it is. Even when the equation is more complicated. So my original equation is x squared equals x plus 1. And I got 1.61803 as a solution. So I can take that number, replace the x's in the original equation with 1.61803, and I should be able to check and see if this is true, right? So let's do it in the calculator. If I do 1.61803 squared, I get 2.618 about. Does that equal what you get when you add 1.618 to 1? (2.618) equals 2.618. Yep, they're equal. If you square it, and if you add 1 to it, you get the same thing, 2.618. All right, so we know that phi makes this equation true, right? I know that if I plug 1.61803 into that equation, that equation will be true. So this gives me kind of a cool little thing that I can do to compute higher and higher values of powers of phi. So if x squared equals x plus 1 has x equals phi as a solution, right? That means that if I plug phi into this equation, it's true. That's what it means to be a solution. Phi is a value that when you replace x's with it, the equation is true. So phi squared equals phi plus 1. Definitely true. All right, so let's say I wanted to know what phi cubed equaled. New question. I want to know what phi cubed equals. Well, I'm going to use some rules of exponents here, so I'll remind you about them as we go. When you multiply, when you have like bases, like a squared times a to the 5th, how do you simplify that? Add. Yeah, when you're multiplying like bases, you add the exponents. So we're going to use this property over and over here. Okay. Another thing we're going to have to do is distribute. Okay, so hopefully we remember how to distribute. So we're going to be using a little bit of algebra here. So if I wanted to get phi cubed, I could multiply phi squared times phi to the first. Do you agree that that's true? Yeah, because we have like bases, phi, so I would add the exponents, 2 and 1. So the reason I wrote it as phi squared times phi is because I know what phi squared is. So I'm going to make a little substitution. I'm going to replace phi squared with phi plus 1 because they're equal. So I can just substitute one for the other. So replace phi squared, and maybe I'll do this vertically. I think that'll be clearer. I'm going to replace the phi squared with what it equals, phi plus 1. So I have phi plus 1. Phi squared gets replaced with phi plus 1, and then I still have times phi on the outside here. This phi just comes along. I'm doing a substitution. I'm replacing phi squared with something else that equals phi squared. I can do that because phi squared and phi plus 1 are equal. They're the same thing. So in my original equation, write it again. Okay, so this came from my imagination. I said if I want to know what phi cubed is, well, I could multiply phi squared times phi. Because I could use the property of exponents that says add the exponents, right? So this came from my imagination. I said I'm trying to figure out what phi cubed is. I know what phi squared is, so if I just multiply that by phi, I'll have phi cubed. All right, then I used the fact that phi squared equals phi plus 1 to make a substitution. So instead of phi squared here, instead of phi squared in that green box, replace it with phi plus 1 because they are one and the same. They're the same value. So this equals, now in this green box, instead of phi squared, I'm going to put phi plus 1. Replaced it. They're the same thing. And then I still have this phi over here that comes down. Okay? All right, now we're going to distribute this phi. You guys remember how to do that? Distribute. So we're going to take the phi and multiply it by both terms in the parentheses. You're probably more used to having the phi on the left, but it works exactly the same. Just distribute it into both terms. Okay, so I get phi cubed. This is just coming down. Phi cubed equals phi squared plus phi. But what's phi squared equal? Phi plus 1. I'm going to make another substitution. Right, phi squared, going to replace it again with phi plus 1. Nope. I mean, yes, we're doing the same step twice, but it's not redundant. It's just the same trick twice. So replacing phi squared with phi plus 1, and then plus phi. Now when I simplify, I get phi cubed. I combine like terms. Phi plus phi is what? 2 phi. And then I have a plus 1. So there's a formula for phi cubed. 2 phi plus 1. So it's a little bit algebra intensive, but not anything that you don't have the knowledge to do. Okay? Maybe we just got to shake off a little rust. Okay? So I think that we should do it again This time we're going to find phi to the fourth. So I know, right, from the last problem that phi cubed is 2 phi plus 1. I want phi to the fourth. So I'm using what I got from the last process to get to my next value that I'm looking for. Okay, so I know phi cubed, I want phi to the fourth. So my first little trick was the property of exponents. I said, well, if I want phi to the fourth, I could do phi cubed times phi. Because the property of exponents says that when you multiply like bases, you would add the exponents. So this is phi cubed times phi to the first. So I could add the exponents and get the phi to the fourth. Vertical. But what does phi cubed equal? Phi squared equals phi plus 1. What's phi cubed equal? 2 phi plus 1. Yeah, it's right here. I just calculated it 5 minutes ago. So I'm going to replace, right, phi cubed equals 2 phi plus 1. They're the same. So I'm going to replace the phi cubed in this equation with a 2 phi plus 1. So phi cubed, instead of that, I'm going to write 2 phi plus 1, and then I still have the times phi. Distribute your phi, right? So I multiply both terms in the parentheses by phi, and I get 2 phi times phi, which is what? 2 phi plus phi is 3 phi. What's 2 phi times phi? Close. What? 2 phi squared. Yeah. 2 phi times phi means 2 times phi, which is 2 phi squared. The phi times the phi gives you a phi squared. And then phi times 1 is phi. But what does phi squared equal? Phi plus 1. Phi plus 1. Yep. So phi to the fourth is equal to 2 times, instead of phi squared, I'm going to write phi plus 1 plus phi. Distribute my 2. So I get 2 phi plus 2 plus phi. Combine like terms. What's 2 phi plus phi? Three. Nope. 3 phi. 2 phis plus 1 phi is 3 phis plus 2. Phi to the fourth. Okay, so we have like 3 key steps here. The first one is I wanted phi to the fourth, so I wrote it as phi cubed times phi. And I made 2 key substitutions while simplifying this. I replaced phi cubed with what it equals, and then I replaced phi squared with what it equals. 2 key substitutions. And the rest was just distributing and combining like terms. So I'm going to keep a little chart here. I'm going to do phi squared, phi cubed, phi to the fourth, and what they equal, right? So phi squared, that was phi plus 1. And phi cubed, we figured that out, that was 2 phi plus 1. And phi to the fourth, that's 3 phi plus 2. Let's do one more, phi to the fifth. I'll do it over here this time. phi to the fifth. Okay. First trick is to rewrite, if I want to know phi to the fifth, I'm going to rewrite it as phi to the fourth times phi, because I know what phi to the fourth is. And just multiply it by phi. Phi to the fourth can get replaced with what other expression? 3 phi plus 2. Very good. We know that phi to the fourth is 3 phi plus 2, so I make that replacement. Instead of phi to the fourth, I write 3 phi plus 2 times phi. Okay, and then I just have to distribute my phi. What is 3 phi times phi? Nope. Closer. Just do the first part for me. Phi times 3 phi. 3 phi squared. It's the phi that gets squared. You were saying 3 squared phi. Right? You wrote it right and just said it wrong. Yeah. So it's 3 phi times phi. That comes out to 3 phi squared. And then phi times 2 is 2 phi. Good. Okay, so now I have a new expression for phi to the fifth, 3 phi squared plus 2 phi. But what does phi squared equal? Phi plus 1. Phi squared, go to my little chart. Phi squared is phi plus 1. So I make another substitution. So I get phi to the fifth equals 2 times phi plus 1. Right? Instead of writing 3 times phi squared, oops, that should be a 3. 3 times phi plus 1 plus 2 phi. That also comes down. Then we distribute the 3. So I get phi to the fifth equals 3 phi plus 3 plus 2 phi. Combine like terms, 3 phi plus 2 phi makes 5 phi. 5 phi plus 3. So phi to the fifth equals 5 phi plus 3. Okay, what I would like you to do, I would like you to try on your own to come up with phi to the sixth. Okay, so I'll just get you started. You know phi to the fifth is 5 phi plus 3. And you know phi squared is phi plus 1. Those are the two key facts you're going to need. I want you to find phi to the sixth. Okay. Follow the same procedure we did for the other 3. Okay, so let's go through it together, finding phi to the sixth. Most people are well on their way, if not there. Okay. So phi to the sixth, we can rewrite as phi to the fifth times phi. Right? We're manipulating that rule of exponents that says when you multiply like bases, you add the exponents. So I can rewrite phi to the sixth as phi to the fifth times phi to the first. Then replace phi to the fifth with what it equals. Right? What does phi to the fifth equal? 5 phi plus 3. So instead of phi to the fifth times phi, I'm going to do 5 phi plus 3 times phi. Okay, make a substitution, replace phi to the fifth with something else that is equal to it. Distribute your phi to the parentheses. 5 phi times phi is 5 phi squared, and 3 times phi is 3 phi. Okay, but phi squared, what does that equal? Phi plus 1, so I make another substitution, 5 times phi plus 1 instead of 5 times phi squared plus 3 phi. Distribute the 5 to your parentheses. So 5 times phi is 5 phi. 5 times 1 is 5. Finally, just combine like terms. 5 phi plus 3 phi is 8 phi plus 5. So this is phi to the 6th, 8 phi plus 5. So if I go back to my table, phi to the 6th is 8 phi plus 5. Could anybody try to predict phi to the 7th without actually doing it out? (13 phi plus 8). Can you explain how you came up with that? Okay, great. So there's several patterns. Yeah. So we saw that the previous coefficient becomes what gets added on as the constant in the next one. Right? So you can pretty quickly predict what you're going to add on next time. So in my next one, the thing that gets added would be 13. Right? And my coefficients, the number in front of the phi, goes 1, 2, 3, 5, 8, 13. Those are Fibonacci numbers. So are the numbers we add on. 1, 1, 2, 3, 5, 8. Those are Fibonacci numbers. I know, right? I told you you would get sick of me showing you applications of the Fibonacci numbers, right? So let's rewrite this table again, because I'm going to try to write a formula for how to raise phi to a number using Fibonacci numbers. So let's see, I've got phi squared equals phi plus 1, phi cubed equals 2 phi plus 1, 3 phi plus 2, 5 phi plus 3, 8 phi plus 5. That should be good enough. So 8. What number in the list of Fibonacci numbers is 8? Where in the list is it? F1, F2, F3, which one? F6, yes. So we go 1, 1, 2, 3, 5, 8, right? It's the 6th number in the Fibonacci list. Maybe it would help if I write them out here. So I've got 1, 1, 2, 5, 8, 13, 21, list of Fibonacci numbers. So 8 is the 6th number in the list. So 8, instead of writing it as 8, I'm going to write it as F6, because it's the 6th number in the list. So F6 times phi instead of 8 times phi. And 5, what number in the list is that? The 5th. 1, 2, 3, 4, 5. 5 is the 5th number in the list. So instead of just writing 5, I'm going to write F5. So let's do a similar thing for each of my equations. So for 5 phi plus 3, 5 is the 5th number in the list. So this is F5 times phi plus 3, which is what number in the list? The 4th. And 3 phi plus 2. Well, 3 is what number in the list? The 4th. So this is F4. Just replacing the 3 with an F4. And 2 is the 3rd number in the list, F3. And then 2 phi plus 1. Well, 2, I'm going to replace the 2 with F3. Because F3 is 2. They're the same value. So F3 times phi plus, could be F1 or F2, because 1 is F1 and F2. But if I follow this pattern, F6 phi plus F5, F5 phi plus F4, F4 phi plus F3, this should be F2, right? If it follows the pattern from below. And then the first one would be F2 phi plus F1. All right, so if I'm trying to write a general formula, like I want to know how could I raise phi to the nth power? What Fibonacci numbers? It's definitely going to be something times, do this better, phi to the nth. It's always going to come out as something times phi plus something else. And those two somethings are Fibonacci numbers. The question is, which Fibonacci number is it? Okay. So when I did phi to the 6th, when n was 6, the Fibonacci number times phi was f6, right? And when I raised phi to the 5, the Fibonacci number in front of phi was f5. And when I raised phi to the 4th, the first Fibonacci number in my equation was f4. So if I'm going to do phi to the n, what Fibonacci number goes in front of phi? The nth. F sub n. And when I did, and then in all of my equations, the first Fibonacci number I used was f6 here, and then I went down one to get the one. So I have f5, f4, f4, f3. Yep, so it's f sub n minus 1. So this is your formula on how to raise phi to the nth power. Do f sub n times phi plus f sub n minus 1. So let's just quickly use this formula to raise, say, phi to the 13th power. So I would want f sub 13 times phi plus f sub 12. Okay, if n is 13, then I have f sub 13 here, and 13 minus 1 is 12, so this becomes f sub 12. All right, so f sub 13, that's the 13th Fibonacci number. So that would be 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233. I think 233 is the next one, 233. Plus F12, which was 144. Mm-hmm. What's your question? No. F13 means the 13th Fibonacci number in the list. So if I were to write out my Fibonacci numbers, I have 1, 1, 2, 3, 8, 13, 21, 34, 55, 89. 55 plus 89 is 144. 89 plus 144 is 233. 377, right? So F13 is the 13th number in this list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I replaced F13 with 233. And F12 is the 12th number in the list, 144. Okay, so that finishes up our class 15 lecture. That was the last bit, was to raise the golden ratio to powers. And it turns out that you use the Fibonacci numbers to do it. Okay, class 16 is where we're going to start to link some of the stuff from last class to nature. It's going to seem a little disconnected at first, but I promise I'm going to bring it back around. Okay. So, what does it mean to say that two objects are similar? Right? Two objects are similar. It means they have the same proportions or the same shape, but different sizes, right? So if somebody took a photograph of me, the picture of me would be similar to me in that they're the exact same shape, but one of them is much smaller than the other, right? Or like a scale size model of a building would be similar to the real building. Two objects that have the same shape but different sizes are similar. Or one is a scaled version of the other. So all the measurements of the second are some multiple of the measurements of the first. So are these two triangles similar? Yeah, how do you know? It's twice as big. They're the same shape. The second one is just blown up by a factor of 2, right? So my scale factor here is 2. Yes, they're similar because every measurement in the first triangle gets doubled to make the second triangle. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. Okay, because you multiply every measurement in the first by the same number, that means they're similar. Scale factor of 2. All right, so let's compare the perimeters of my two similar triangles. I know these two guys are similar. The symbol for similar is just one squiggly line. So you can put it in if you want. These two triangles are similar because they have a scale factor. All right, so let's look at the perimeter of triangle 1. How do you find the perimeter of any geometric object? Add them all up. Its perimeter is the distance around. So we have 3 plus 4 is 7, plus 5 is 12. And then the perimeter of triangle 2 is going to be 6 plus 8 plus 10, which is 24. So what do you notice about the relationship between perimeter 1 and perimeter 2? Double, right? It's the same factor as all the lengths, right? So these two triangles are related in that every length in triangle 2 is 2 times the length from triangle 1. Same relationship holds for perimeter. Same scale factor. Let's look at the areas of the two triangles. Anybody remember how to find the area of a triangle? Divide what by 2? Yeah, and it is. Yep. So if this were, I could put these lines in. Imagine they were there, and then this would create a rectangle, right? Area of a rectangle is just base times height, which would be 3 times 4. But the triangle is only half of that, so it would be divide by 2, and you get 6. You get 1/2 3 times 4. Oops. 1/2 3 times 4, which is 6. Okay. And then the area of triangle 2, I could do the same trick. Make this into a rectangle. Base times height would be 8 times 6, but the triangle is only half of this rectangle, so it's 1/2 times 6 times 8. Which is 24. So how are the areas of the two triangles related? What's their relationship? Is it double? It's quadrupled. Yeah. No, but that's a good conjecture. It's not double the scale factor you used before. It's your scale factor squared. No, so not times 2, but raised to the 2. Yeah. Yeah. So my area has scale factor 4, right? 6 times 4 gives me 24. And the 4 came from taking my original scale factor and squaring it. And kind of a good way to remember this is that area is a 2-dimensional measurement, right? So you square your other scale factor. It's 2-dimensional. So that's just a real fast overview of similarity. Okay, two figures are similar means that all the lengths in the figure have the same scale factor. So does the perimeter, and the area has the scale factor squared. Yes. So in two similar figures, all the lengths and the perimeter, because the perimeter is just a length also, right? It's just a distance. All the lengths and the perimeter have the same scale factor. Let's call it S. They have the same scale factor S. The scale factor for the areas of the two figures is S squared. Whatever the scale factor was for the lengths, you square it. That's your scale factor for the areas. All right, so suppose that these two triangles are similar. So I'm telling you that these are similar. I'm not asking you whether or not they are. They are. So I have a 3, 4, 5 right triangle. I want to find the other two sides of the big triangle as well as the area and perimeter. So what's my scale factor here? 5. Yeah, so hold on, so I looked at the two corresponding sides that I had, and I said, well, this side is 3 and this side is 15, so it must have been a scale factor of 5, right? 3 times 5 would give me 15. Okay, so I'm going to write scale factor is 5. Because you just have to ask yourself, what did I multiply 3 by to turn this into a 15? It would have to be 5. So then you multiply all your other lengths by 5. 4 times 5 is 20. 5 times 5 is 25. Okay, and then the perimeter of this little triangle is 3 plus 4 plus 5, which is 12, which means without having to add it, what's the perimeter of the big triangle? Yeah, 12 times 5, 60. Yep, and then the area of this guy is 6. We calculated it on the previous slide. And the area of this triangle is going to be, instead of 6 times 5, right, it's 6 times what? 5 squared. The scale factor squared. 6 times 25 is 150. And you can check both of those. You could just add up 15 plus 20 plus 25, you get 60. And you could do 1/2 times 20 times 15, and you would get 150. Okay, so we did this little review of similarity to help us understand this new concept of something called a nomen. A genome, yeah. It's pronounced nomen. It's a nomen to a figure is a connected figure, another figure, which, when attached to the first figure, yields a figure similar to the first figure. What? Right. Okay, so once we do it, once I draw a picture of a gnomon, it'll make a lot more sense. Okay, so here is a rectangle, 1 by 2 rectangle. So imagine that you know, you're building something in your garage, right? And you just cut out a piece of plywood that's 1 foot by 2 feet. And you just finished cutting it and you go, shoot, I meant this thing to be twice as big. I really wanted a 2 by 4 rectangle. Instead of starting over and wasting this piece of plywood, I could cut out an L-shaped piece of plywood that I could glue to that guy that would make a 2 by 4 instead of a 1 by 2. So what I really want is a 2 by 4. So I'm gonna cut out a new L shape that I'm gonna glue to this guy to make this twice as big as it was. Okay, so I want 2 by 4, so I need this to be twice the length, so I need that to be 1. And then I need this to be 2, so that I have 2 across and 4 down. No, that's another way I could do it. Yeah. So this sort of fixed to my problem, this L shape that I could glue to my original messed up piece of plywood, that's called a gnomon. Okay, this L-shaped thing, this is an L-shaped gnomon. Okay, it satisfies the definition of being a gnomon is because it's a figure that when I glue it to the first figure, my 1 by 2 rectangle is similar to the big glued together rectangle. The whole thing. Yep. So if I draw, yeah, so I'll put my 1 by 2 right here. My 1 by 2 is similar to the whole glued together piece. So the gnomon is the piece that you glue on to make the glued together thing similar to the original. So this L-shaped gnomon would have dimensions 1, 4, and 2. 1 and 2. So you'd have to go cut an L piece of plywood with those dimensions. Now, so the whole idea was not to waste plywood, right? We don't want to waste our wood. So cutting an L is going to waste wood, right? Because then you're just going to throw away a piece this size. So another way that we could do it is to not use an L, but use another rectangle itself. So it's also possible to add a gnomon that's also a rectangle. Yeah, so I would go like this, 3 units this way, and 2 units down. And now my glued together, my 2 pieces glued together, make a 2 by 4 rectangle, which is what I was looking for. It's just turned on its side, right? So my 1 by 2, for me, it helps to draw these 2 things vertically so you can see the same shape or draw them in the same orientation. So my original 1 by 2 is similar to my new glued together thing, which if I turn on its side, looks like 2 by 4. Here's my gnomon. So you can see that the glued together thing and my original are similar. So this shaded area, the part that I put on, is called a rectangular gnomon. So what kind of shape would be a gnomon to a circle? So if I have a circle, I want to glue something onto it that creates a bigger circle. A ring. Yeah. So I would glue on a ring. If I started with a circle, I cut out a piece of plywood that was circular and I thought, oh shoot, I wanted this circle to be bigger. What I would glue to it is like a donut. Why you wouldn't just cut out a bigger circle is, I don't know. But you would use a ring or a donut, whatever you want to call it, or a washer. All right, so triangles that have angles 36, 72, 72 can make a nice family of gnomons, and we can draw them. So we'll do it by hand first, and then I'll have a computer program do it much more neatly. So here's my triangle, 72, 72, 36. My three angles add up to what? 180. The three angles of a triangle always add up to 180. And two angles that make a straight line supplement, they also add up to 180. So I'm trying to make a gnomon. So I'm going to glue it to this thing so that I get another triangle that has angles 36, 72, 72. So I'm going to start by drawing that straight angle. So if this piece is 72, what does this piece have to be? Close. A straight angle is 180 degrees. So I already have 72 degrees of that. So to get the other part, I have to do 180 minus 72. 180 minus 72, 108. So this angle here has to be 108. And then up here at this angle, I'm going to copy it. I'm going to create another 36-degree angle. And then extend the two pink lines that I started until they touch. Okay. So 36 and 108 means I already have 144 degrees in that triangle. So the three angles of a triangle always add up to 180. So my last angle would be 180 minus 144, 36 degrees. So this last angle here has to be 36 degrees because the three angles of my triangle have to add up to 180. So I glued on this pink triangle, glued it on. It's 36, 36, 108 are its angles. When you glue it to the original, we have 72 degrees. What's this angle here? 72. 36 and 36 makes 72. And then my last angle, 36. So I've created, when I glued them together, this outer green triangle is a 72, 72, 36 triangle. So that green triangle is similar to my original blue triangle. It's just turned on its side. And I can do this forever. I can keep doing this. Every 36, 72, 72 triangle, you can create a gnomon by using a 36, 36, 108. So on one of my 72-degree angles, I'll do one more. On one of my 72-degree angles, make a straight line. This angle would have to be 108 to make a straight angle. On my 36-degree angle, copy it, 36 degrees. Extend these two lines until, oops, It doesn't seem like they're going to touch. Let's do these two up top. I'm going to copy this one over here. And then this would be 108. I'm going to extend these two blue lines until they touch, which is going to be pretty far away. I'm going to cheat. They'll eventually cross, right? And this is 36, 108, which means this one's going to have to be 36. And the big triangle is going to be 72, 72, 36.
If you attach the line parallel to the hypotenuse anywhere on the line, and just made a trapezoid in that.
So this is my awfully drawn version of the family of gnomons, but precisely because I run out of room too quickly to draw a lot of them for you, I have an electronic version. Okay, so here's my my 36, 72, 72 triangle. And I purposely started it with it pretty small because the picture gets big quickly. So I drawn my first gnomon, 36, 108, 36 triangle. So that creates, right, 72 degrees right here, 72 degrees right here, and 36 degrees here. So this glued together triangle is similar to the green triangle. Same shape, just turned on its side. So then I'm going to do another one. And now my glued together big triangle, this guy, is similar to the green one. It's just rotated and bigger. And then if I do a third one, now we've got 72 here, 72 here, and 36 here. So this big triangle, same shape as the original green, just bigger and rotated. And if I do one more, now I have a big giant triangle that's again 72, 72, 36. So I can just keep doing this forever and getting bigger and bigger versions of this little triangle. So you probably will not be surprised to learn that this is called a golden triangle. Why? Because the ratio of one of the long sides to the short side is always 1.61803. No matter how big you draw this triangle. Right, so let's look here. I can have Geometry Sketchpad, that's the program I'm using, measure a distance. So I go measure distance. So the longer leg of the green triangle is about 3.57 centimeters. And then we do the shorter leg. Measure how long that is. It's 2.21 centimeters. I want to calculate why I can't. Calculate. I want to do the longer divided by the shorter. Ooh, 1.61803. And then let's do it for the really big triangle. If I do the long leg, find its length. And then the shortest side of the really big triangle is this one. And then I want to calculate the longer divided by the shorter, 1.61803. It rounded to 2 decimal places, but it was 1.61803. So no matter how big you make that triangle, the ratio is always the golden ratio. So we call it a golden triangle. What was that?
Can you make a gnomon that's not a triangle? Like if you made a line parallel to that say, like in this line, it's parallel. I've made it like regular trapezoid.
Mm-hmm. Yes, there could be gnomons that are not also triangles. It's also a gnomon. It's just not part of the cool family that we were drawing that spirals. Yeah. Right. All right. So we've seen that every rectangle has an L-shaped gnomon. You can, if you make your piece of plywood that you cut too small, you can always build an L to put onto it and make it the right size. The question is, some rectangles have a square-shaped gnomon. And we want to figure out what kind of special rectangles have a gnomon that is a square. Okay, so here's my original rectangle. We'll call it 1 by x. I want to attach a square to it so that these two are similar. So that my original rectangle is similar to my new glued together rectangle. So I attached an x by x square here, right, onto my original. And I turned it on its side so that you could see the similarity, right? Short, short, long, long. Okay. So for the x by x square to be a gnomon to the rectangle on the left, it has to be that this guy is similar to this guy. Since they're similar, we can write a proportion, right? We can do short to short equals long to long. When you divide any two corresponding pieces, you're going to get the scale factor. Okay. So the short side of this rectangle would be what? 1. What's the short side of the glued together rectangle over here? X. Yep. Yep. Raised to x. The long side of my smaller rectangle on the left, x. The long side of this rectangle is 1 plus x. That equation look familiar? That's the equation we solved to originally find the golden ratio when we were trying to decide where to cut a line that would make it the prettiest. So this is x squared equals 1 plus x. We know the equation to the solution to this equation is x equals 1.61803. So rectangles that have square gnomons are golden rectangles. Only golden rectangles have square gnomons. So that's our conclusion here. Only golden rectangles. So that's a rectangle where length divided by width is the golden ratio. Only golden rectangles have square gnomons. Yep, sure. So the rectangles that have square gnomons are golden rectangles. That's the same summary I just put before. How much time? I have 2 minutes and just enough time to get through this. Okay. So Fibonacci rectangles are rectangles where the length and the width are consecutive Fibonacci numbers. Okay, so for example, could have a 5 by 8, because 5 and 8 are two Fibonacci numbers that are next to each other in the list. Or we could have 2 by 3. 2 and 3 are Fibonacci numbers right next to each other in the list. Or 8 by 13. So these are Fibonacci rectangles. Any rectangle whose lengths are consecutive Fibonacci numbers. Are they golden rectangles? Is the length divided by the width equal to the golden ratio? So last class, we saw that when we did ratios of consecutive Fibonacci numbers, what do we get? We approached the golden ratio, right? The further out we went in the list, the closer we got to 1.61803. So Fibonacci numbers, Fibonacci rectangles are almost golden, right? The bigger the Fibonacci numbers, the closer to golden they are.